Our last section for this chapter will be covering Kepler's laws. Kepler deduced his 3 laws from a scientist named Tycho Brahe. So we're going to do a little bit of history about each of these 2 men. As a young man, Tycho Brahe vowed to become an astronomer when he saw a solar eclipse. He thought that was really cool, and so he decided that's what he wanted to do with his life. And 3 years later, he saw 2 planets in conjunction. This means that they were lined up with each other. However, the date that had been predicted by books for this event to occur was actually off by 2 days. So Tycho Brahe decided not only was he going to study astronomy, but he wanted to dedicate his life to making accurate predictions for astronomical events. So he kept studying and he traveled for about 5 years. And then in 1576, the King of Denmark gave him his own island, and the name of that island was called Ven, so that Tycho Brahe could build an observatory and work towards his goal. Tycho spent the next 20 years there recording the exact positions of the planets and the stars. And then in 1597, he moved to Prague so that he could look at his data and try to come up with some ideas on how the universe worked. Although Tycho Brahe was really enthusiastic, he was having a little bit of difficulty making his data line up with the math that he was trying to use to figure out what the universe looked like and how the planets traveled around. So in 1600, he hired a budding young mathematician named Johannes Kepler, and Kepler became Brahe's assistant at the age of 29. Kepler felt strongly that he could use geometry and math to explain 3 things. 1, the number of the planets. 2, their distance, so how far apart were they from the sun and from each other. And 3, the motion of the planets. What was the shape of their orbits? The main point of contention between the 2 is that unlike Brahe, who believed that the Earth was the center of the universe, we call that geocentric, Kepler formed a sun-centered or heliocentric model. They actually disagreed on this point so much that they got into a huge fight, and Brahe kicked Kepler out and wouldn't let him have any of his data. It turns out later that Kepler actually went back and stole all of Tycho Brahe's data after he had died, and he did in fact use all of that information to form his 3 laws. So it actually gave him proof for the theories of what he thought the planets would be behaving like. You are going to have one more video to watch on YouTube, and it's going to have some questions that go with it that will give you a little bit more information about the historical background for Tycho Brahe and Johannes Kepler. So just be looking for that in your Google Classroom assignments. But let's get to Kepler's 3 laws. Kepler's first law states that the paths of the planets are ellipses with the center of the sun at one focus. And you'll see in the video that you're going to watch that the data that Tycho Brahe had taken actually showed that the planets don't line up in a perfect circle around the sun. So Kepler used that data to show that the planets actually orbit in an elliptical pattern around the sun. And when we say at one focus, an ellipse has 2 points that are called the foci, and each planet will orbit around the sun being placed at one of these 2 positions. And fun fact, the word focus in Latin actually means fireplace. So since the sun is made of fire, it's appropriate that it's placed at a focus of an ellipse. Kepler's second law states that a line from the sun to a planet sweeps out equal areas in equal time intervals. Now, I know you don't have a textbook, so we're going to scratch this out, but I did include a picture of what that figure would look like at the bottom of the screen. So we want to have the sun at one focus, and the planet is going to travel in an elliptical pattern. When we talk about a line from the sun to a planet sweeping out equal areas in equal time intervals, let's consider a planet at this position, and then a certain time interval later, it ends up in this position. So if we were to draw a line from the sun to a planet at each of those and shade in that area, that's going to equal one area. Well, if we look on the opposite side of our orbit, the planet can move from here to here in that same amount of time interval. So we're looking at equal times, and then we would draw a line from the sun to the planet and shade in that area. Kepler's second law is telling us that those two shaded areas are in fact equal to each other. Another way that we can think about this is that the planet will move fastest when it's closest to the sun, and it's going to move its slowest point when it's farthest away. And the reason for that is because of that gravitational pull. So gravity is pulling stronger when the planet is closer, because there's less of a distance in between them. So think about that universal law of gravitation. If that distance were increased, there would be less of a gravitational force applied. So the planet can move faster, closer to the sun, and slower, farther away. And this picture just gives you another idea for maybe a planet that's not quite as elliptical in shape. So it's a little bit more circular, but notice that the sun is still off center a little bit, and each of these shaded areas are going to represent equal time intervals for the planet traveling around its orbit, and then the areas are in fact equal for each of those shaded spots. Kepler's third law is the only one we're going to work with that has an equation. And it states that the square of the ratio of the periods of any two planets revolving around the sun is equal to the cube of the ratio of their average distances from the sun. And you can also use this law to compare, say, moons or artificial satellites orbiting a planet, not just planets orbiting the sun. A reminder, capital T is the variable for period. R is going to be the average distance to the sun. And notice that it's an average because things do travel in an elliptical pattern. So it's not an exact same radius because it's not an exact circle. So we're looking at an average distance to the sun, or the thing that we're revolving around. The A's and the B's refer to your two different objects doing the orbiting. So we're going to do an example problem so that you can see how this ties together. So your example states that the moon has a period of 27.3 days and an average distance of almost 4 times 10 to the 8th meters from the center of the Earth. We're going to find the period of a satellite in orbit that is a certain distance from the center of the Earth. So we're comparing these two objects. So I would suggest making a chart. So I'm going to say that the moon is my object A and my satellite is object B. Both of these are orbiting around the Earth. So the period of the moon, which would be T with a subscript of an A, is 27.3 days. The average distance between the moon and the Earth is 3.9 times 10 to the 8th meters. And then for my satellite, we don't know what the period is, so I'm going to put a question mark for the period of object B. You are given the average distance of the satellite to the Earth, and that is 6.7 times 10 to the 6 meters. Remember our formula from up above, so I'm going to switch screens and plug in the numbers. Kepler's third law equation actually looks like this, but I'm going to distribute those exponents. So I'm going to say that the period of object A squared over the period of object B squared is going to be equal to the average distance of object A cubed over the average distance of object B cubed. By distributing the exponent on both sides, I can simply cross multiply. So I'm going to go ahead and do that before I plug in any numbers. This would give me TA squared times RB cubed equal to TB squared times RA cubed. And I'm interested, remember, in the period of object B, so I'm going to divide and put my TB squared on one side. So that's going to leave me with TA squared times RB cubed over RA cubed. And now I'm going to plug in my numbers, and because the period is squared, I will take the square root at the end. So my formula looked like this. and I'm going to plug in the period of object A, which was 27.3 days. That's going to get squared. And then the average distance for object B was 6.7 times 10 to the 6th meters cubed. And the average distance for object A was 3.9 times 10 to the 8th meters cubed. Because both of my distances were given in meters, I did not have to do any conversions. And also, once they're cubed, these meters cubed are going to cancel with those meters cubed, and that's going to leave us with days squared equal to our period squared. Now at this point you could type in everything in your calculator all in one step, so if you're really good with parentheses and confident in your calculator skills, you can go ahead and do that. I'm going to go ahead and write out each number, and I'm going to square this number and write that down. I'm going to cube this distance and write it, and then I'm going to divide, and I'll write down what the second distance cubed was equal to. Once I type in those numbers, I should get 745.29 times 3 times 10 to the 20th, and then I'm going to divide those by 5.932 times 10 to the 25th. That gives me a number of 0.003779. However, remember that was equal to the period squared, so I do want to take the square root. And this will give me a final answer of 0.06 days. You don't have to change that to seconds. You can leave it in the same unit as the other period that was provided at the beginning of the question. So you should get a final answer of about 0.06 days. Again, if you have some difficulty with typing in to your calculator such large numbers, make sure you come in and get some help before your test, because you are going to need to know how to solve one of these problems.